Our next speaker is the foremost expert in graph databases and large-scale analytics. Please welcome the CEO of Blazegraph from SYSTAP, Bebee.
Thanks, everybody. Appreciate the opportunity to be here. Can everybody hear me okay in the back? All right, great. If I get too quiet, just stand up, jump up and down, do something to get my attention. So, very excited to talk to you about graph analytics, graph database applications today. What I would say is that I would appreciate it if you guys are interested, make this an interactive session. If you have questions, pop up. We'll try and take them as we go through, and I'm sure Eric will keep us on schedule. So, with that, I wanted to start off and give you a little bit of context. When we talk about graphs, we're thinking about graphs of the data structure, so edges and vertices, nodes and links. Graphs show up in all kinds of different important applications. And as it turns out, anytime that you want to represent complex dependencies in your data, graphs turn out to be a very good representation to do that. So don't just think about social networks or communication networks. Think also about biological networks, protein pathway networks, time series-like applications. And so graphs are a really important data structure for machine learning, deep learning applications, as well as information management type approaches. One of the challenges that when graphs get very large, and you'll see on the right-hand side a sort of map of the internet circa 2006, they become these complex data structures that challenge existing platforms and computational models to get good performance out of them. So our vision as Blazegraph is to produce scalable software to help people solve graph problems at a variety of levels, from embedded graph databases to high availability graph databases to GPU accelerated solutions. And this is a quick snapshot of sort of where we see our market space. We have an open source platform that gets downloaded sort of hundreds of times a week. Our biggest spaces are in life sciences, where people range from precision medicine applications that are using graph-based approaches to integrate information, to cancer genomics research, where people are looking at using protein pathway network graph mining to try and identify new cures and solutions. In the finance space, we see applications ranging from master data management to trade counterparty data analytics to compliance applications. Information management is historically a very rich graph space, and so we're being used by the Wikimedia Query Service. We have a lot of cultural heritage applications, such as the British Museum, and that's a very, very rich area for us. And then an emerging area is sort of Internet of Things. People are finding that graph models are really useful when you have lots of sensors producing lots of different data, and you want to try and make sense of what that information is. So, and then finally, cyber analytics, both in the defense and the commercial space, so it's a classic sort of graph application. So to talk through a few of our sort of largest customer use cases, precision medicine, by far outside of cyber is sort of one of the biggest spaces. And this application really is about graph-based data integration. And so you think about a hospital, think about treatment areas. You have lots of different data coming from lots of different systems. And you want to be able to produce better treatment outcomes by allowing people to integrate the data and ask questions about it in a common way. And so one of our customers, a company called SYSTAP, based out in the Bay Area, is building a precision medicine platform to do this. You may have seen them, they were mentioned recently in President Biden's Moonshot for Cancer type campaign. And they're essentially doing ontology-based data integration. They use the Sparkle query language underneath. And they've developed their own domain-specific query language for precision medicine to be able to integrate this information and then provide the users, in this case, largely the healthcare practitioners, an ability to query this fused information. From our perspective, it's a cool application, but it also highlights the scale of the problem. So today, their largest customers are 5 to 10 billion edge graph applications, and their own internal projections put their customers moving mid to late next year into the 100 billion edge graph range. And 100 billion edges is a little bit larger than you can handle today on conventional platforms. So they need to look at new approaches and new techniques to be able to do this. activated in these networks. And these kinds of approaches are inherently graph-based, and they're very much very promising in terms of being able to actually treat the ways that cancer is occurring rather than some other approaches. And so we have a lot of research customers doing this space, and this is a very big and growing application space for us. Switching over to knowledge graphs, graph-based applications allow you to actually answer questions and not just search text. And so, as I mentioned earlier, this is a very classic information management graph approach. But we're being used by the Wikimedia Foundation. We have other applications. Yahoo 7 in Australia has sort of a neat application. What they're doing is they're providing soap opera video content that they're producing. And they run named entity extraction and event extraction over the text transcripts of these soap operas. And then they provide a social graph search over it. And so you can ask questions like, show me the soap opera episode where Brad went to the database camp at the UN and gave a talk. And by doing that, then you achieve the 200% increase in time on site by having that application. So not something that I would have considered, but something that they got a good result from. Other applications, the British Museum and Research Space, which is a collaboration with the Carnegie Foundation and the British Museum, they have a mission to be able to provide access to the public for a large number of cultural artifacts. They have a very limited amount of physical real estate to be able to present these artifacts, and so they're looking at ways that they can use knowledge graphs to allow people to experience and share these cultural artifacts in a virtual way. And so this is a very interesting application. They combine it with things that are graph-based, but they also combine it with things like virtual reality and 3D experiences. So you can navigate using metadata to find a particular Greek sculpture from a particular period, and then go into sort of a VR 3D type facility where you can go and look around it as if you were actually in the museum looking at it. So very interesting use cases.
Question?
Yes?
Quick question. Your database is mostly retrieval-oriented, or it supports all the maintenance, insertion, deletion, and update operations?
So the question was, is our database simply retrieval-oriented, or does it also support update and database management operations? And the answer is our graph database platform is a fully asset-compliant database, and so we support transactions, we support sort of full lifecycle database management. We also have other capabilities on top of it that really are supporting more purely graph analytic type use cases, but the core platform is a fully functional graph database. And so just one other example before we talk a little bit more about the technology. Cyber applications, obviously a big graph space, and lots of different cases, if you're looking at net flows, for example, as a boundary of a network or other type of alerting information. Lots of different opportunities to try and understand what's going on in your network by doing graph analytics. And so iterative graph analytics are very important in the cyber defense space. The image here is actually some publicly available net flow data that had a PageRank algorithm run over it using our GPU accelerated platform. And the visualization is from one of our partners, a company called GraphStreet, that also uses some GPU accelerated visualization approaches. But in terms of being able to help understand what's going on in your network, graph analytics are a very important way to do that. So one of the things that for you guys that are involved with software products, you'll know that every customer does some kind of evaluation of your platform. You don't always get a chance to see it. And so in kinds of things that when you're sort of on your journey of building a graph application that you need to that you implement, Blazegraph has APIs and features to help you support that. Our high availability platform uses a shared nothing type architecture. So we use Zookeeper to do coordination between the high availability nodes. There's an election. All of the rights are directed to the leader. And then we use a very low-level replication, which is coordinated through Apache River to be able to support the synchronization between the high availability nodes. This mode also supports online backup and transaction logging. And so, for example, we have a lot of customers that are deployed in EC2. We encourage them to take advantage of the instance disks on their EC2 applications for the higher I/O performance. But yet, of course, you need the durable storage that you can get on your EBS volumes. And so, in this kind of configuration, you can configure your core data on the instance disk and keep your snapshots of backup on your durable storage. So, why is scaling graphs hard? This is really looking at the challenges that graphs aren't like other big data problems. And so you can't just stick a large graph into CPU RAM. Graphs have properties of non-locality and data-dependent parallelism. So as you traverse a very, very large graph, you're having to constantly page in and out of main memory. So even though your CPU cores may be very, very fast, they end up sitting there waiting for the data to come in. And we call that condition, sort of in the marketing speak, the graph cache thrash. But if you look at this chart, what you're looking at on the x-axis is the access latency per clock cycle for various different types of cache and ultimately main memory shown on the y-axis. And what you can clearly see is that when you get out of cache on the top and go into the red line, you're paying almost a 5x performance penalty. So this is really why existing architectures don't scale cost effectively for large graph traversals.
Quick question.
Yeah.
Can you say graph cache thrash 3 times fast?
Graph cache thrash, graph cache thrash, graph cache thrash. How was that? I'll have to practice.
Maybe more interestingly, can you just repeat the explanation for why you don't pay that price when you're still in L2 or L2 cache versus main memory?
Well, so iterative graph analytics often have to touch almost every node in the graph. So if you think about something like PageRank algorithm, you're going to, as you do your iterations, you're going to have to touch every node. And so you're well beyond, if you have a large graph, you're well beyond the size that's going to stay in cache, which is where the CPU really, really excels. And so because of essentially the main memory bandwidth differences between CPU platforms and other architectures, the GPU and then also things like the power architectures.
You're just showing the latency.
Yeah, this is just really looking at the latency. It becomes a latency plus a main memory bandwidth bottleneck.
It's not like going to local cache. Somehow benefit your architecture.
Yeah, I mean, we could have a deeper discussion about it. Ultimately, we think that there are some parts of graph analytics problems that are very well suited towards staying in CPU cache, particularly where there's a lot of locality in the graph. And so, ultimately, we think the best solutions that we'll be seeing in the future are hybrid, sort of many-core GPU or other accelerators plus CPU solutions, so you can really take advantage of the benefits of both architectures.
And you are GPU.
Yeah, we are GPU-based, and so kind of one of the ways that you measure large graph traversals is something called a gigatep, and a gigatep is the ability to traverse 1 billion edges. In this case, we're looking at what is the hardware cost to achieve a gigatep of performance. And so on the far left-hand side is just sort of our baseline. Carnegie Mellon did for the NSA an experiment about 2 years ago, or maybe 3 now, called the NSA Big Data Experiment. They looked at using a large Hadoop Accumulo instance to do graph traversal over a very large scale free graph. They got linear performance over time, but they were only able to achieve about 240 million traversed edges per second. And that just really speaks to the concept that any kind of disk-based approach for iterative graph analytics is just not the right paradigm to use. And so you can see it's quite an expensive way to go. If you look at the Cray XMT2, which is a little bit older, but still a very popular graph architecture, very elegant hardware architecture, based on their published Graph 500 numbers, and Graph 500 is one of the major benchmarks for supercomputing in graphs. We estimate that's about $180,000 per gigatep. And then we did on a cluster of 64 Nvidia K40s a couple years ago, presented at the IEEE Big Data Conference. A scale-free graph, we achieved 32 gigateps. And at that estimate, it's about 16K per gigatep for hardware. And the Pascal architecture, if anybody are GPU junkies, you'll know it was announced at this year's Nvidia GPU Technology Conference. Pascal does a couple things. It increases the amount of RAM on the chip, and it also increases the main memory bandwidth for GPUs up to about 720 gigs a second. And so the Pascal further drops that architecture or the cost advantage down by a fourth. And so you can see that the performance opportunities for GPUs on large graphs is very, very compelling. So we have two GPU accelerated products. The first is what we think of as sort of a classic accelerated platform. So you take our graph database, has the same RDF Sparkle, Blueprints, Tinkerpop support. You add appropriate GPU hardware and appropriate licensing, and you're able to get 200 to 300x query acceleration for your most data-intensive queries. This is largely based on technology. Oh, go ahead. Question in the middle.
Just mentioned this before that memory is constrained for the graph.
Memory bandwidth is one of them.
They have a GPU that's still the biggest constraint. It has to swap the whole memory to a GPU.
Well, when you're actually processing, so if you look at like a Xeon has about, theoretically has about 60 gigs of memory bandwidth. And you put it in a specific card and that drops, but theoretically that's about 60 gigs. And a K40, the current Nvidia K40 or K80 has about 240 gigs a second of memory bandwidth. So once you factor out actually getting the data onto GPU RAM, the performance, it becomes largely a memory bandwidth question. There's a lot of other details related to graph partitioning and how do you do multi-GPU pieces and minimize your communication costs. But so that's really where a lot of the performance benefit is coming from.
The time performance comes from computing side of the GPU rather than memory transport.
Yeah, so one of the things, if I can repeat the question says, does the performance come from the memory performance on the GPU, right? And so one of the GPUs are obviously very hot these days, and a lot of the applications you see are deep learning applications, and they're really taking advantage of a different part of the GPU. So they're taking advantage of the compute side of the GPU. Graphs aren't really compute bound, and so graphs are memory bandwidth bound. So we're taking advantage of the relative memory bandwidth advantages on the GPU.
Can you talk about your partitioning strategy, or is that a little bit beyond the scope of this?
Let me answer that. I've got one question just back over there, and then I'll come back to that briefly. Go ahead.
What, can you get about 4 gigs of RAM on a GPU these days?
The N40 supports 24 gigs of RAM on a single GPU card, which is about, in our testing, is about a 450 million edge graph. To lead into your question, we do a two-dimensional partitioning currently for multi-GPU implementations. And if you think of a P by P grid, across every row are all of the in edges, and across every column are all of the out edges, and that gives us nice logarithmic performance with respect to communication costs.
And what if you have more nodes than, you said, 240 million?
Yeah, so that's really where I'm a little bit off track here, but that's great. So one of the things that I mentioned the Pascal architecture earlier, and so I was talking about it in terms of RAM on the card, as well as the memory bandwidth. There's two other things that are important with Pascal. One is there's something called NVLink, which is a higher throughput bandwidth between the main memory on the CPU and the GPUs. And then the second is that they have the ability to do shared memory. So previously, if you were in a GPU world, you had to think only of the memory on the GPU, and there's a lot to do that you if you're into the graph database world, you'll probably be familiar with the Lehigh University benchmark, the Lumen benchmark. It's sort of the granddaddy of conjunctive query graph benchmarks. It's a parameterized benchmark. Parameterization is the number of universities. So U1000 here is a simulated run of 1,000 universities. The data generator basically generates a university that has students. Students take courses. Courses are taught by faculty. Students are advised by faculty. The Sparkle query you see up here on your left is Lumen query number 9. This is the Sparkle query language if you're not familiar with it. And it's essentially asking the question, show me all of the students that take a course that's also taught by their advisor. And so if you look at the time on our CPU platform, we get about 173,000 results in about 54 seconds. Executing the same query with GPU acceleration, same results, just a little under 200 milliseconds. Now, actual mileage varies, and in full disclosure, not every query benefits this much. The kinds of queries that benefit are, heavy conjunctive join queries where you have to touch a lot of data to evaluate the query. And so these kinds of things are very, can get a lot of acceleration. And so I've got 5 minutes left, so I'm just going to kind of click over a couple of these. We love comparing to Apache Spark. It gives great numbers. And so this is some work we did over the ICWSM 2010 Twitter graph. This is a 2 billion edge graph of Twitter's followers that you may be familiar with. Suffice to say, in all cases, we were much, much faster. This was compared against a single fat node with dual K80s, as well as a 16-node K40 cluster compared to 16 large EC2 instances. So the performance benefit is there. What we see is the problem is this, is that the people who can get the performance benefit out of this hardware are not the same ones who understand how to write analytics and applications. And so we really see the opportunity is to provide ways to give you abstractions to get the power and performance of these hardware platforms without having you to be some kind of parallel programming or HPC expert. And so for iterative graph analytics, we created something called Blazegraph Dazzle to do this. And DASL is sort of an acronym that we pronounce Dazzle. And the goal is to be as easy to use as Apache Spark in terms of being able to get your data, do something quickly with it, but to deliver the performance that you can get out of GPUs and optimized GPU hardware. What Dazzle is a domain-specific language written in Scala that provides linear algebra primitives and graph operations in the Scala language, which has a binding onto our runtime. And so when you write a Dazzle program, we then execute it in a set of optimized CUDA kernels. We also do code generation for user-defined functions, so you can write user-defined functions in Scala. We generate the code, we build the CUDA kernels, and we execute that over a multi-GPU infrastructure. And that's really the core of what Dazzle does. And so it lets you get the power of the GPU platform, but stay in a very comfortable sort of Scala linear algebra-based graph analytics environment. The other thing that's really important is we've done a lot of work with this over the years. And it's cool to be 1000x faster, but if it actually takes you 3 days to move the data from your system to the GPUs, then you really haven't won. And so a big part of the design goal with Dazzle is to be able to integrate and co-opt existing data ecosystems. So this really started off with the sort of Spark RDDs, and then we kind of quickly moved into the data frames world, and that's really where we're working right now. So we provide utilities and libraries, so if you have your data in data frames, we can take that and easily load it into the Dazzle platform to be able to really reduce that sort of end-to-end cycle time. So what does a Dazzle algorithm look like? This is just a very, very simple Scala example. One of the things that we did, I don't have the slides here, but we did some work recently looking at relative code complexity versus performance. And so the page rank, if you look at it in the GraphX Scala implementation, Spark is about like 51 lines of Scala code if you do a naive counting and ignore white space. And our implementation of PageRank is about 53 lines of Scala code. So we're pretty much, if you think that lines of Scala code is a reasonable approximation This is just kind of a quick example. And with that, I think I've covered all of my main points. I've got about a minute left. Is there anything that I'll leave this up so we can take a look at examples of things that work for Dazzle. But other questions?
Just to very quickly clarify, so are you essentially a software solution when you provide this?
Yeah, so we're all a software solution. Currently, our GPU accelerated platforms only work on Nvidia GPUs. We're of course interested in other many core hardware platforms strategically.
You mentioned that there is a two difference you mentioned that in terms of the time, like 187 milliseconds.
Yes.
So now the difference is that what are the cost variances between two? Like of course there is a time variances you mentioned that, but what is the cost variances between these two?
In terms of the hardware cost perspective, we didn't really look at it from that perspective. I mean, it depends on the size of your graph, but you can get a reasonably sized GPU card for several $1,000s that will add on to that. So it's certainly not the same kind of hardware cost difference that you're talking about with the Hadoop comparison versus the GPU one. So I didn't talk to this slide. I think this is the last question Eric's telling me. So these are examples. What we see is that there's been really a convergence between what you think of as traditional graph, which you'll see on the left-hand side, so community detection, triangle counting type applications, and things that you start to see on the right, which are sort of machine learning and k-means, clustering type applications. These are all examples of things that can be expressed in Dazzle, the domain-specific language-driven scale-up, on our platform. And so it's really much more than just graph, traditional graph, but that's kind of where we see it. This is essentially a picture into our product backlog. But thank you very much. I'm about to get the hook. So.
Thank you very much. We are now going to take a break for lunch. This is also a great time to speak with any of the prior speakers, or if you can find the ones coming up. Lunch is out that door up there before everybody gets up. It's that door. You go outside and make a big U-turn to the right, and you will see lots of food. So we will resume in 30 minutes at exactly 1 o'clock. That's 1 o'clock we will resume. Thank you.